Here we are. Question number 26 reads, what forces are responsible for stabilizing the primary structure of a polypeptide and or protein? So that's taking into consideration something that's 20 amino acids long, as well as something that's 800 amino acids long. We've got A, hydrogen bonding, B, covalent bonding, C, ionic bonding, or D, none of the above. The best answer for this question is going to be B, covalent bonding, because a peptide bond is what stabilizes that, but a peptide bond is an example of a covalent bond. So covalent bonding does stabilize that. Number 27, within the secondary structure of a protein, beta sheets can form as parallel or anti-parallel beta sheets. Select the best answer regarding that information. Okay, anti-parallel beta sheets are stronger due to shorter hydrogen bonds. Parallel beta sheets are stronger due to shorter hydrogen bonds. Parallel and anti-parallel beta sheets are equal in strength. And D, none of the provided statements are true. Okay, so parallel and anti-parallel beta sheets. Okay, are they equal in strength? No, they're not. Now, so that's going to dismiss C as an answer option. So sorry, see ya later. Anti-parallel beta sheets are stronger, and it is because they have shorter hydrogen bonds, because the groups they're more directly across from one another, so the hydrogen bonds aren't really staggered like this. The hydrogen bonds between my fists, they instead are like this in an anti-parallel beta sheet. Okay, so the correct answer for number 27, and again, I'm checking my key here, is A. 28, the tertiary structure of a protein can be stabilized by all of the following forces except covalent bonds, ionic bonds, hydrogen bonds, hydrophobic interactions, or E, all the forces listed help stabilize tertiary structure of a protein. Okay, covalent bonds. Yep. A disulfide bond is a covalent bond. Ionic interactions or ionic bonds. Well, an arginine can interact with a arginine cation can interact with an aspartic acid anion, so that's an ionic interaction. Hydrogen bonds, yep. Serine and a threonine could interact. Hydrophobic interactions, oh yeah. Leucines, isoleucines, they're going to be glad to interact with one another. So that leaves behind for question number 28, E is the best answer. A Ramachandran plot displays the combination of blank and blank bond angles, which are favorable for a polypeptide to attain. Okay, a combination of A, phi and peptide, phi and theta, chi and phi, or the correct answer, phi and psi bond angles. Number 30, which of the following statements is true? I got to check my... Okay, good. Yeah, I'm on the right. Which of the following statements is true about peptide bonds? A, peptide bonds are highly flexible and enable proteins to fold into multiple different 3D shapes. Well, peptide bonds are inflexible. They are rigid. Peptide bonds are resonance stabilized and extremely rigid. Ooh, that's interesting. Peptide bonds are an example of a hydrogen bond. No, a peptide bond is an example of a covalent bond. Peptide bonds can result from a precipitation reaction. Ooh, that's an interesting idea. A reaction. We did talk about a reaction taking place. And what we talked about was a condensation reaction. That was responsible for forming a peptide bond. So B is our best answer. Peptide bonds are resonance stabilized and extremely rigid. I'm going to go back to question 31, the top of the other side of the paper. The average alpha helix consists of approximately how many amino acids? Okay, so this is the length of an alpha helix. How many amino acids make up that alpha helix? And the correct answer is 10. Now, that doesn't tell anything about like the dimensions in the X, Y, and Z planes that it takes up, but that's what it is. 32. So that was number 31. C, yeah. Okay, you've purified a protein with a 110 amino acid region that you believe forms an alpha helix and spans a lipid bilayer. The lipid bilayer is approximately 40 angstroms thick. how many amino acids of this 110 amino acid region would be necessary to span that 40 angstrom region? Okay, so what we're getting at here is we need to know basically, here's our lipid bilayer. This is 40 angstroms. How many amino acids will make a helix that spans that region? Okay, so basically, how many coils? That's one way. There's multiple ways that you can approach this. How many coils will span this? And the way that we can figure that out is we could say one rotation or one coil rotation is 5.4 angstroms. So I'm going to say 40 divided by 5.4 gives me, we're looking at about 7.4 rotations. Now, one rotation is 3.6 amino acids. So 7.4 times 3.6 gives us 26.64. So that's one way that we can solve this question. And you know what, for this question, what I'm going to do, I'm going to, rounding. We round 26.64. We would round that up to 30. So there's part of me that wants to be super rigid and say it's 26.6. You round that up to 30. C is the correct answer. But I didn't give any guidelines about rounding and ideas about rounding and what's the best thing to do. Is there a minimum threshold? So you know what? I'm actually going to accept B and C for this. So if you answered B, great. If you answered C, I'm gonna say better, because that's a better answer. But that's that. Good? Good. Okay, so B or C will be accepted. So I gotta go back and hand grade that one. Number 33, which amino acid is known to be a secondary structure breaker due to it being, quote, too flexible? Well, our major breakers are glycine and proline. Proline because it's super rigid, and glycine because it is too flexible. Question number 34. The work that was prepared by Chow and Fassman was substantial because A, it supported the idea that with primary structure information, you could predict secondary structures. Supported the idea that the primary structure information, you could predict tertiary structure. Supported the idea that secondary structure information, you could predict tertiary, and secondary could predict protein-protein interactions. They took primary structure information and basically came up with a way that you could model for, make a pretty strong prediction about secondary structures. So the correct answer for that is B. They drew the connection between primary and secondary. When comparing protein sequences, what is an example of a conservative substitution? Okay, so conservative substitution is something where the amino acids that are mutated for one another are not that drastically different. And if we say asparagine and glycine, glycine is a non-polar amino acid, asparagine is polar. Aspartic acid, tryptophan. We're talking about two polar residues, but one's negative and one's neutral. Tryptophan and cytosine, well, cytosine's not even an amino acid. Cysteine and cytosine, again, cytosine's not an amino acid. The correct answer for that would be B, aspartic acid going to glutamic acid. All right, well, that's going to wrap up this video, and I'll see you in the next video.